As you can see here, for the sake of comparison, I have drawn a cylinder whose wall thickness is clearly much lesser than the wall thickness that has been shown in this cylinder. So, relatively speaking, this we can call as a thin cylinder, whereas this we will be calling as a thick cylinder. That is just at the first visual glance of these two cylindrical pressure vessels. Now, as we have dealt with this ratio in the thin cylinder topic, if the thickness to the internal diameter ratio is less than or equal to 1 by 20, it is called a thin cylinder, and if this T by D ratio exceeds 1 upon 20, it means it is considered as a thick cylinder. Now, these two ratios, or this ratio, is actually a rule of thumb, and different textbooks have slight variations in the numerical value of this ratio, some as wide as T by D being compared to a ratio of 1 by 10 to 1 by 20. Nevertheless, we will keep this ratio of 1 by 20 as the dividing marker between thick and thin cylinders. Also, we have briefly discussed in the introductory video of thin cylinders that in case of a thin cylinder, we will only consider the hoop stress and the longitudinal stress. The radial stress is neglected because of the thin wall of the cylinder behaving like a membrane. It distends, and therefore the radial stresses are negligible and can be omitted. Whereas in case of the thick cylinder, we must consider the three stresses perpendicular to each other. So, let us look at the key points. Thick cylinders are used to sustain high pressures compared to thin cylinders. Second, any stress element in the wall of a thick cylinder, such as this stress element, any stress element in the wall of a thick cylinder is subjected to a mutually perpendicular triaxial principal stress system. Mutually perpendicular triaxial along three axes principal stresses are normal stresses system. So, I have drawn that here, marked out the xyz coordinate system, and I have shown this is the element that is a part of the wall of the thick cylinder subjected to three mutually perpendicular principal stresses. This is sigma L longitudinal stress, hoop stress, and the radial stress. So, these are three stresses, and we cannot neglect any of them. Sigma R is a new entry from the thin cylinder where we neglect this, but here we have to calculate. So, the key difference here in thick cylinder is we are considering radial stress. Second important point is the radial stress and the hoop stress, they are not constant across the thickness of the wall, which means sigma R will vary from this to this point. Sigma H also will vary from this to this point. This is the thickness of the element or the wall. Sigma H and sigma R are not constant across the thickness, whereas the longitudinal stress is constant across the thickness. So, those are the key points that are pertinent to thick cylinders. Now, there are a few assumptions in the theory of thick cylinders. Some standard assumptions like the material is homogeneous, isotropic, and Hooke's law is valid. All of that is uh, those are assumptions that are important, but then I have only written a key assumption which has to do with the longitudinal strain and stress. So, this in fact is a very important assumption, and it keeps repeating itself in the theory of bending and also in torsion. So, let us see what this is. Plane sections remain plane under pressure, which means plane sections remain plane before and after the application of fluid pressure, which means this is a plane transverse section. Upon application of the fluid pressure, even if this gets elongated, there is no distortion in the plane of this section. That is the meaning of it, which means the longitudinal strain of this remains constant. The longitudinal strain remains constant. Uh, I have drawn this section here, and I have marked three different radii. One is R1, second is R2, third is R3. So, no matter where we take the value of the longitudinal strain, it is independent of the radius at which we are trying to find out longitudinal strain. So, the key point is the longitudinal strain is constant, which also means the longitudinal stress is constant. Longitudinal strains at R1, R2 and R3 are the same. Okay. So, this is a very important assumption. The longitudinal strain and the longitudinal stress both are constant. So, here we write sigma L, which is the longitudinal strain, which is constant, and I have drawn the stress element again, the longitudinal stress, the radial stress and the Hooke's stress. So, we know this is the generalized Hooke's law, epsilon L is equal to sigma L by E, sigma L being the prime stress causing the strain in the longitudinal direction. Now, the strain due to this and this stress is given by minus mu sigma h by E minus mu sigma r by E. So, taking mu common, we rewrite this equation, taking 1 upon E is common for the whole terms, and we write sigma L as constant. So, this whole term sums up to a constant number, but sigma L is constant, E is a constant number for a material, mu is also constant, and sigma L we know is constant. Therefore, it is imperative that in this entire equation the sum of these two terms must also be constant. Alright, since all these terms are amounting to a constant value and they are not dependent on the radius, it is imperative that the sum of sigma h and sigma r are also constant. So, therefore, we conclude sigma h plus sigma r is constant and we call it as 2a, say. You can take it as any other term, but for the sake of mathematical ease, this has been equated to twice of a. This is equation number 1. We are going to make use of this equation in the next video. Okay, students, we will proceed with the second video in the thick cylinder topic. This is actually the basis of the entire design, analysis and design of thick cylinders. It is called the Lamy's theory for thick cylinders. Lamy is the French scientist who is responsible for deriving the suitable equations which are used in the design of thick cylinders. Now, what we have here is a cross section of a thick cylinder. The black lines represent the inner and the outer boundary of the cylinder, and what is shown in the red arrows inside is denoted as Pi. Pi standing for internal pressure, and external pressure is shown as P naught. All right, and as you see, there is an elemental ring marked in the blue, which is situated at a distance of r from the center of the thick cylinder. The inner part is at r, the outer part is at a radial distance of r plus dr. The thickness of this elemental ring is small dr. Okay, so that's the geometry. This is a pressure vessel subjected to an internal pressure Pi and an external pressure E naught, and we are taking an elemental ring for the sake of analysis. Now, of this entire circular ring, I have only shown a hemispherical portion and the length of the cylinder is L. So, this what I have shown here is actually this ring. So, what do we have here? This ring is subjected to pressures on either side. Now, one must note that this thickness of the wall is being compressed. As a response, the elemental ring will try to push outward. This is a very key point. The internal external pressure are applied in a compressive manner. In order to stay in equilibrium, the elemental ring will try to push outward. So, there is a inward radial pressure acting here and there is an outward radial pressure acting here. That is what I have shown here. So, the inner part of this elemental ring is having an inward radial pressure and the outer part is having an outward directed radial pressure. All right, now this is defined as r, and the outer part is defined by the radial distance r plus dr, and this is the hoop stress acting along this portion. Okay, the hoop stress actually acts for the entire length. Now what else? This we are going to call as radial pressure sigma r, and the outer pressure is sigma r plus d sigma r. The idea being, at a distance of additional distance of dr, the radial pressure also is changed by a small amount dr. Okay. So what is the bursting force? The bursting force is the pressure, this elemental ring. This elemental ring could be the entire thickness also, or it could be located at any particular distance. Remember, r and r plus dr are variables. You can plug any number in this. So the point is that the difference of these pressures may cause the wall to burst open. So the bursting force is stress into area. What is the stress into area? What are the pressures that we're looking at? This is the stress, and what is the area of this outer curved surface? The area of this outer curved surface can be taken as a projected area, like we have taken for thin cylinder curved surface. So what is this total length from this outer point to this outer point? We know this is the radius r plus dr. So from here to here it is r plus dr. From here to here is also r plus dr. So that is 2 into r plus dr into this length is L. So this portion is stress, this portion is area. So that becomes force. Force in the upward direction, outward direction. Then there's also the inward stress. Now what is the magnitude of stress here? Sigma r. What is the projected area of this inner curve? It is nothing but sigma r into this radial distance is r. So that's r and r, 2r into the length is L. So the difference of these two forces is what is called the bursting force. Then the resisting force is due to the hoop stress. So the difference of these two pressures is equilibrated by the hoop stress that is acting at the bottom of this cylindrical cut wall. That is equal to sigma h into 2 into dr. This is dr and this length is L. Okay, so equating this force, which is the bursting force, to the resisting force, you get a lot of terms. The 2L's get cancelled, and then upon expanding you get these terms. Notice r sigma dr minus r sigma dr get cancelled, and the product of d sigma r and dr, the d sigma r is small, dr is also small, so the product becomes even more small, that can be equated to 0, and then we are left with these terms, and we rearrange these. After this you divide the entire equation by dr. So sigma r dr by dr and r d sigma r by dr, sigma h into dr by dr, and then you get this equation. So rearranging terms, we write this and then we call it equation number 2. But we know this is equation number 1, sigma h plus sigma r is equal to 2a. If you go back to video number 1, the last portion, I have derived this equation from the assumption that plane sections remain plane before and after applying pressure. So sigma h plus sigma r is equal to 2a. I substitute instead of sigma h 2a minus sigma r. So 2a minus 2 sigma r. Why 2 sigma r? Because I get 2a minus sigma r, there is one more minus sigma r, so I get minus 2 sigma r is equal to r into d sigma r by dr. Now I multiply the entire equation by r, so I get 2ar minus 2r sigma r minus r square into d sigma r by dr is equal to 0. Okay, we leave that equation and we just consider a function. If a function y is equal to ar square minus sigma r into r square, then its first derivative with respect to dr is equal to, the derivative of this is 2ar minus, this is these two terms are in terms of r, so you have to do the differentiation in by parts. So minus 2 sigma r into r minus r square into this derivative, which is d sigma r by dr. This is actually the rate at which this changes, sigma r. All right. So, if this is a function, then its first derivative is this value. But this equation is nothing but this equation, and that is equal to 0. So, going back to this, we see, when will the first derivative be equal to 0? When the original function is a constant. If you have a function which is constant, then its derivative will be 0. But this is equal to 0. Therefore, this function ar square minus sigma r into r square is constant. Now, we ascribe the alphabet capital B to this constant, and therefore, we get, taking r square common, a minus sigma r is equal to b, or sigma r is equal to a minus b by r square. We call this as equation number 3, and this is the expression for radial stress. Again, from equation number 1, instead of sigma r, we write sigma r is equal to 2a minus sigma h, and substitute this 2a minus sigma h instead of sigma r in equation 3. The equation 3 becomes 2a minus sigma h is equal to a minus b by r square. So, you get the expression for hoop stress, which is sigma h is equal to a plus b by r square. So, this is equation number 4. Equation number 3 and equation number 4 are called Lami's equations for thick cylinders. Finally, let us look at some key points. Equation numbers 3 and 4 are known as Lami's equations for thick cylinders. Lami's constants A and B can be evaluated from boundary conditions of internal and external pressures or maximum permissible stresses in material. So, these points will become clearer when we solve numericals. Okay. So, in these two equations, sigma r is equal to a minus b by r square, sigma h is equal to a plus b by r square. A and b are constants, Lami's constants, and their values can be obtained by applying suitable boundary conditions of internal and external pressures. Third point, for design of thick cylinders, hoop stress at inner radius is considered since it is maximum. Now, notice the hoop stress is a plus b by r square. So, sigma h is inversely proportional to the radius. So, as radius reduces, sigma h increases. So, the inner radius, sigma h will have maximum value. That is what we have written. At inner radius, sigma h is maximum. Next, radial pressures are considered negative since they are compressive. That is just a sign convention. Compressive pressures are taken as negative. The internal and external pressures are radial pressures and are also taken as negative. So, when we solve the problem in the next video, whenever we encounter internal and external pressures, we have to take them as negative parameters. Now, we are going to.
So this is a small problem where you can do this one also. So these are the basic things that for a circular hoop, to find out the hoop stress and longitudinal stress, which are called as normal and tangential stresses in a tube or a cylinder, can be calculated using the previous videos formulas. So the same thing we can find it in strength of materials textbooks also, where you can understand the basic concepts of the stress calculation. So this problem actually will help you to find out the stresses internally and externally, and what is the use of that also you can understand. Okay, so for this problem, it is better you do this, follow this problem also along with the previous videos. It will be useful. So if you want, you can take a screenshot in between the explanation also.
To see a couple of problems on the thick cylinder. A thick cylindrical pipe of outer dia 300 millimeter and thickness of metal 50 mm is subjected to an internal fluid pressure of 40 megapascal and an external pressure of 2.5 megapascal. Determine the maximum and minimum intensities of circumferential and radial stresses in the pipe section. Plot the stress variation across the pipe cross section. So if you look at the given data, we have been given the outer diameter of the cylindrical pipe. It is all clearly mentioned thick cylindrical pipe, and the metal thickness is given. So if you add 2 times the metal thickness, outer dia is 300 and the inner dia would be 200 millimeters. There is an internal fluid pressure of 40 megapascal and an external fluid pressure of 2.5 megapascal. Now we must realize that these fluid pressures are radial pressures and they must be considered negative. I have explained this in the previous video. We have been asked to find out the minimum and maximum circumferential, that is hoop, and radial stresses in the pipe section, and also plot the stress variation. So here is the diagram. What we have been given is the outer diameter of 300, thickness is 50 mm. So therefore, if we were to find out the inner diameter, subtract 250s out of 300, so inner diameter is 200 millimeters. So DO for outer dia 300, so the radius to the outer circumference is 150 mm, inner diameter is 200, inner radius is 100 mm, thickness is 50 millimeters. Now this is the information regarding the pressure that is given. At inner radius, that is at 100 millimeters, the radial pressure is 40 megapascal and we have to consider it as negative. At radius of 150 mm, that is reaching to the outer part, the external pressure is given as 2.5 megapascal, which we will be taking as negative. Now the solution, we invoke Lami's equations. Radial stress is equal to A minus B by R square and hoop stress is equal to A plus B by R square. So the radial stresses, we have information on the radial stresses. These both are radial stresses. So we write this in the Lami's equation, A minus B upon R inner square, that is 100 square, is equal to minus 40, A minus B by 150 square is equal to minus 2.5. Both are expressions for radial stress. We solve them simultaneously and we get the value of B and we get the value of A. Once the Lami's constants are obtained, we can plug them into the hoop stress equation and find out the values at inner and outer radial distances. So we are now calculating the hoop stress. Sigma h is equal to A plus B by R square. At R is equal to 100 mm, inner dia, that is at this point, sigma h is equal to the value of A 27.5 plus 675,000 by 100 square, and we get the value of hoop stress is 95 megapascal. At the outer radial distance 150 mm, substituting A and B and the radial distance of 150, we get 57.5 megapascal. Now we have been asked to plot the stresses. So I have drawn a hemispherical part of the transverse section of the pipe, and this is the inner radius 100 mm, this is outer radius 150 millimeters. Now notice that I have plotted the variation of hoop stress on one limb of the section, and on the other limb I have plotted the radial stress. But it is clear that each limb will have both hoop stress and radial stresses, but drawing it on the same side will make the diagram look clumsy. So deliberately these two stresses have been plotted on different parts. So here the inner radial at the inner radius the hoop stress is 95 megapascal and the outer radius it is 57.5, and one must note that the variation is parabolic because the hoop stress is inversely proportional to R square. Similarly, the radial stress variation is shown here, the external pressure being 2.5 and the internal pressure is 40 megapascal. Now, you must note that there is a plus sign ascribed to the hoop stress variation because hoop stresses are tensile in nature and radial pressures are compressive in nature. So, therefore, there is a negative sign ascribed to this. We will look at one other problem. This is a design problem. A thick cylinder of internal dia 200 mm is subjected to an internal fluid pressure of 14 Newton per mm square. If the allowable stress in tension for the material is 120 Newton per mm square, determine the thickness required. So, the thickness of the pressure vessel is not known, but what is given is there is an internal fluid pressure of 40 megapascal and the material stress in tension cannot go beyond 120 Newton per mm square. The internal diameter is given. So, let us look at the diagram. We do not know the thickness, so the thickness is marked as T. Internal diameter is 200 millimeters. So, the internal radius is 100 mm and the external radius is 100 plus T millimeters. Internal dia is 200 mm, radial distance to the inner is 100 mm, and at inner radius we know that the internal fluid pressure is radial pressure, and that is minus 40. Sigma AT, that is the allowable tensile stress in the material, is 120 megapascal. We have been asked to find thickness. This is a very important point. What are we going to do with this allowable tensile stress? We know that the hoop stress is going to be the maximum of the two types of stresses, and also the hoop stress is given by sigma h is equal to a plus b by r square, which means sigma h is proportional to 1 upon r square. So, at the lesser value of r, sigma hoop h assumes higher value, which means hoop stress will have maximum value at the inner radius compared to the outer radius. We know hoop stress at inner radius governs the design. So, we are equating the hoop stress to the allowable tensile stress. Now, we are invoking the radial stress and the hoop stress. Radial stress equation is A minus B by R square. At the inner radius, we know the pressure is minus 40. This is the internal fluid pressure, and the hoop stress is A plus B by R square, which is 100 square, is equal to allowable tensile stress 120 megapascal. So, if you solve this simultaneously, you get A is equal to 40 and you get B is equal to 800,000. Now, notice that there is no mention of external pressure. In such cases, we take external pressure is equal to 0 at a radial distance of 100 plus T. So, there is an internal pressure that is mentioned at the inner radius, which is 40 megapascal, but the external pressure is not mentioned, in which case we take P is equal to 0. So, again substituting it in the radial stress equation, A minus B by R square, R here is 100 plus T, the pressure is 0, or A is equal to B upon 100 plus T whole square. Now, substituting the values we have obtained for A and B, 40 and 800,000, we get the value of thickness required as 41.42 millimeters. Now, in practical situations, this value is normally rounded off to a multiple of 25. So, normally it is taken as 50 millimeters.
So this is the class. You can actually go to the